All right, welcome everyone to another seminar. It's my pleasure today to give you Vito Scarola from Virginia Tech, who's visiting us for a couple of days. We're lucky to have him here in person. Vito got his PhD with Janandra Jain, working on fractional quantum Hall in where's Janandra? Penn State. Yeah, sorry. And then after a postdoc with Shankar Sarma in Maryland and with Matthias Troyer in ETH, joined the faculty of Virginia Tech. And today he's going to tell us about his latest research. Thank you, Vito.
Yeah. Thanks for the introduction and having me here. It's been great meeting with folks. So yeah, I'm from Virginia Tech, and I'm going to be talking about strong interaction effects in lattice models. So this is kind of ideal calculations for experiments that we're interested in. So does it work for me to use, I'll use this laser pointer for the online community. There. So I can change slides there. So I'll just tell you a little bit about my group and things that we're interested in before I talk about a couple works that I'm interested in. On the left is my group. I had 4 postdocs. My one postdoc went to work for a quantum consulting firm, actually, so we're still doing research together. So he's technically not part of my group, a couple grad students. And these folks are some of my co-PIs, which kind of give away the outline of the talk almost, quantum information, and a lot of AMO experimentalists. If you don't know who they are, I'll talk a little bit about AMO in a bit. So we have, so we're funded by the DoD, and we think a lot about new quantum states of matter. Can we realize them in the lab? We compare our numerics and theory with what's going on in labs. And we also make predictions for proposals for experiments. We're going to talk about a couple of proposals. And one of the things I'm most interested in is if you get to real strongly correlated systems, can you get emergent physics? I'll describe what I mean by emergent. And if that, in other words, can things pop out at you that you wouldn't expect? Another part of my group looks at classical and quantum algorithm development. So we're thinking about quantum simulation in particular. And we're looking at that in the context of solving strongly correlated problems like the Hubbard model. I'll just briefly mention a couple of recent works that we have before I talk about the 2 topics we wanted. One set of algorithms that we're thinking about, and this is actually data on the left here, is to realize an algorithm that's efficient, doesn't need error correction on a quantum device that can actually measure the spectral function of complex models. So we've been working on that, both classical algorithms and other algorithms. This is a plot of the spectral function as a function of frequency. The peak there tells you the gap of a model you're interested in. And it turns out it doesn't need too much, doesn't need error correction, you can get nice results. So we're excited about that. Other part of my research is in something called measurement-based quantum computing. If you've never seen it before, it's interesting. It's these squares here indicate measurements on what's called a cluster state or a graph state. The idea is you can program a measurement-based quantum computer through measurements and execute an algorithm. In this case, we're time evolving the Hubbard model. And it doesn't look like it, but we are. So that's what that community is interested in. I'm interested in that partly from the quantum simulation perspective, but also because graph states are fascinating. Many body phases have a lot of properties that overlap with the quantum information community. So that's another set of topics. But the primary thing that we think about is strong correlation, models that are connected to atomic, molecular, and optical systems, so AMO. And often in that community, this is called quantum analog simulation. And there, what that means is you build an experiment that replicates a strongly correlated problem like the Hubbard model, like a fractional quantum Hall model. And you try and see if you can get an observable that tells you more about the model. So it's an experiment that's, in a sense, doing a simulation. The reason we can think about that is that these experiments, I'm briefly just going to talk about how they're set up so you can understand motivation for some of the models I'll be looking at. The idea is that you take ultra cold gas bosons are either fermions. So boson would be rubidium-87, for example. It's the most common. Potassium-40 is the most common fermion. So the sphere here represents quantum degenerate gas. And you can shine external lasers on them. And if they're counter-propagating, they set up a standing wave pattern. The standing wave pattern induces an AC Stark effect, which creates a potential energy landscape. You can have all sorts of geometries like these 1D tubes. Other examples, when you have different counter-propagating configurations, you can get lattices, like a three-dimensional cubic lattice shown over here. What's different from solids, well, there's many things that are different. Particles are hopping around in this lattice. There's no disorder, conventional disorder. There's no lattice phonons. And in these systems, you can solve this single particle band structure exactly. It's an analytic problem that we teach students. So it's pretty nice. It's called the Matthew problem. And that means we have pretty well controlled experiments. I'm a theorist and I study these experiments partly because the models are well defined and you can directly connect with experiments. Pretty nice. So what I'm going to talk about today are some models motivated by AMO experiments. And these are called flat band models. I'll explain what that is in a second. In the context of these cold atom experiments, we can, as I'll advertise, generalize some physics from the quantum Hall effects and things we've seen there. And in the two works I'm going to describe a flat band generated from spin-orbit coupling. So you may have heard that flat bands can be made from twisted bilayer systems is one example method with graphene, and most famously. What I'm going to point out here is that you can do this with spin-orbit coupling and get what's called an emergent Luttinger liquid. And I'll explain what I mean again by emergent there. And then if I have time, I'm going to talk about two-dimensional lattices where there is a flat band, but a quadratic band touching point gives you an interesting opening of an energy gap that leads to what's called a topological non-insulator. So if I have time, I'll talk about that too. So just a little background on what I think is interesting about flat bands. So I've been thinking about this for a long time. And the original flat band, if you will, the interesting one, was in the thought about in the context of the quantum Hall effects. The quantum Hall effect, integer quantum Hall effect, discovered by von Klitzing. Let me just describe the experiments very quickly. Two-dimensional electron gas, source a current, perpendicular magnetic field, and you can measure the longitudinal and Hall voltages. You expect a classical increase of the resistance as fewer states are below the Fermi level, but what was found is that there's plateaus, that's the red curve here, quantized at E²/h in this Hall resistance. It was also found as concomitant dips, that's the green here, where you see like zeroing actually of the resistance. This is plotted as a function of perpendicular magnetic field. And so what's going on? How do we understand that? So the idea here is that if you take a non-interacting electron and solve the Schrödinger equation, you get discrete energy levels called lambda levels. They're spaced by the proportional to the magnetic field. And as you increase the field, if the Fermi level is fixed, fewer levels are below. That means you can carry fewer and fewer electrons to engage in the current, and the resistance goes up. But you get plateaus because, let's say, you start at 3 guys below the Fermi level, and as you increase the magnetic field, then 2 guys are below the Fermi level, and then you get to 1 level below the Fermi level. So this, as you can see, these dashes are an energy level, but each dash corresponds to orbital that the electron can occupy. And they're all at the same energy. So I'm calling these lambda levels a flat band. And in fact, the number of electrons, when it's equal to the number of flux quantum, we say that we have new or filling 1. So there's 1 electron per flux quantum or per orbital. And so that's a partial explanation for how the plateaus work, just a cartoon there. You might wonder why there's 0 resistance. So what's happening there is that along the edge, the gap goes to 0 because you have confinement. And you can get what are called chiral currents. So the magnetic field breaks time reversal symmetry and it forces the current to flow in a specific direction. So you can see these arrows here. They're depicting flow in a clockwise direction set up by a magnetic field. And the only way the current can move in these samples, because the bulkous gap is along the edge, a chiral current forced by the magnetic field. And that, interestingly, sets up a no backscattering situation so that you get no resistance or resistivity here. So this resistivity goes to 0 as a result of this suppression of backscattering. So that qualitatively explains the data. A lot of work done on that over the years. What's remarkable is that they increase the magnetic field in Dansu and where Stormer did this. And they found something really remarkable, that at the lowest lambda level, where you have a partial filling, so fewer electrons than available flux quanta, they found an energy gap that you can see in this plateau here. This is their original data, and they shared the Nobel Prize for this. What's surprising is that there's a quenched kinetic energy. So if you imagine writing a Hamiltonian, there's no kinetic energy term. There's just a Coulomb interaction between the electrons. But somehow, all the electron-electron repulsions set up this phenomena of the quantum Hall effect. I'm citing Bob Laughlin's work in 1983 down here. This is not his famous paper where he defined a wave function that explains the quantum liquid, and he shared the Nobel Prize for this explanation, the quantum liquid at one-third filling. What he proposed in this paper is a starting point for modeling the system, which is that the flat band is where you think about where to do your calculation. So in this paper, he's proposing a flat lambda level as a starting point, non-perturbative limit. What he's saying is that the fractional quantum Hall effect is the most strongly correlated problem in condensed matter. You have no small parameters, no perturbation theory. And once other people made a mistake to not do that, including Anderson and Flatsman and so on. Laughlin first proposed this way of thinking about things. We now know that even though you have no kinetic energy, there's quite a bit of physics. There's been over 70 fractions found so far. Each fraction has its own different spin structure and collective mode. So this is an example piece of physics. This curve here was actually done by Haldane in 85 as the first evidence for a collective mode near one-third filling. So he's plotting energy thanks to the Coulomb interaction in a flat band as a function of wave vector, implying that the Coulomb interaction is setting up some sort of waves and sort of emergent kinetics, if you will. After many years of developing theoretical tools, we now know how to understand these modes. This is energy versus wave vector, and this curve here is a calculation we can do with variational wave functions that have been validated. And what they correspond to is rotons. You create an exciton of a quasi-particle and quasi-hole formed from these quasi-particles are called composite fermions. So sometimes they're called CFs. And we know, or we can calculate what those energies are. These circles over here are data for different fractions. And the wiggles, each wiggle corresponds to what's called a roton. And the data were collected by launching surface acoustic waves and doing photoluminescence. And so the wiggles from the calculation match up with the rotons found in an experiment. So we, in other words, can make a comparison between theory and experiment, and up to a shift, these curves agree. So we're pretty happy about that because we understand the shift through disorder. And so the collective modes were emerging in a flat band. It's entirely due to interactions. So that's pretty interesting. Other ground states have been found beyond these uniform liquids that I haven't really showed you a wave function for, but there's paired states, stripes, and bubbles have just been found at Purdue. We predicted those a long time ago. So we're pretty, in the quantum Hall effects, all that physics is happening in a flat lambda level band. And so what I've been thinking about over the years is whether or not lattices or something similar can have a flat band. We can switch on the interaction and see something analogous. So that's the sort of message or theme of the talk. So what do I mean by a flat band in the context of a lattice? We have translational invariance, and we then think of the energy as a function of wave vector. And on the left, I just plotted like a conventional weak lattice parabolic dispersion, where you think about the kinetic energy plus the interaction, right? And they compete. You can do perturbation theory. But if you have a flat band and the Fermi level just populates this flat band either fully or partially, and the interaction energy scale is within the gap to the other states, then the Hamiltonian, P here is a projection operator, is just projecting the interaction into that band. So what we wanted to think about is if there are lattice models relative to the AMO setting that can project the interaction in this flat band and then show or have interesting physics pop out of there or emerge. And this is what I mean by emerging. There's no small parameter. You can't do. It's hard to do mean field theory, if at all, and you don't expect the physics from the non-interacting life of a particle in the flat band to come out because there is no non-interacting or kinetic energy component to the model. So that's what I mean by emergent. It's a non-perturbative problem. So what I'm going to talk about is an example where we looked at 1D and we found interactions in a flat spin-orbit band can actually generate an emergent Luttinger liquid. So that's what I'll talk about next. Just a little background on the experiments that are motivating the model I'm going to show you. In AMO, they've been able to do something remarkable. They've been able to make synthetic spin-orbit coupling in lattices. So the idea is you have a particle moving in a coordinated potential energy landscape set up by laser. They've been able to add additional lasers that couple to the momentum to the spin. The circle is depicting an atom, and it's got internal hyperfine states. And you can then associate an arrow with a pseudospin. So you have two pseudospins. And what happens is that the counterpropagating lasers, it was originally proposed by Dan Stamper-Kern, is that they couple the momentum to the spin. So there's technically a Zeeman effect, but there the Zeeman term really can be written down as a momentum kick given to one pseudospin that then is different from the momentum kick given to the other pseudospin. And this is what we call a spin orbit type coupling. This is implemented and now seen in a lot of labs. Ian Spielman's group, Marilyn Ketterly's group, many others have implemented spin orbit coupling in the lab. And it's synthetic. The strength of the laser actually determines the strength of the spin orbit coupling. So it can get quite high, actually, in comparison to a material where you just find some material and then it's got some spin orbit coupling. It may or may not be strong. Bismuth, I think, is one of the more strongly spin orbit coupled systems. But we asked, what happens if you add a Zeeman term to a spin orbit coupled term? It turns out we can flatten the band there. And by flat band here, I mean not a trivial flat band where the lattice is very deep and the particles can't move. What happens is that the kinetic energy gets quenched when you crank up the spin orbit coupling strength by tuning up the strength of the laser. And it can actually cause the single particles basis states to interfere with one another. So there's effectively no dispersion. So the particles don't move, they're inert, but they're still quantum mechanical in that they can overlap. So this is a plot of the energy as a function of wave vector for this model. This is a 1D model of a particle hopping in a continuum model, a lattice. This S here is the wavelength, the depth of the laser of wavelength L or KL, wave vector KL. And the idea is that the laser can be tuned up in strength and this lattice can get deeper. You end up with a tight binding model, and the spin orbit term and the Zeeman term can be tuned to give you a flat band. So this calculation shows the band structure nearly flat, actually. And that's a regime we're proposing you can work in. There's two modes, chi plus and chi minus, associated with the two spin components. And so the question we asked was, well, if you can build this flat band from spin orbit coupling, what do the interactions do? In a cold atom experiment, the atoms don't have a Coulomb tail like electrons do. They just have a contact interaction. They're just hard spheres. So most of the alkalis are like that. And we model the interaction through a pseudopotential. So G can be tuned, actually. They can control that. And what we argued in this work is that you can project the interactions into a flat band. So U is a conventional Hubbard type term, and P is the projection into that flat spin orbit term, flat spin orbit band. And what we found remarkably is that because the spin orbit coupling is flattened, but nonetheless the states are still quantum, they're bulbous, if you will, and they start to overlap. These wave functions overlap, and the interaction which was normally on site then gets turned to be nearest neighbors. So here I'm just plotting the interaction as a function of inner site separation. And you can see that if the particles have nearest neighbor occupancy, there's an energy penalty for one particle to be here and one to be here. And by particle, I mean a spinor eigenstate. So this little green circle here depicts an eigenstate of a spin-over coupled problem. So that's why it's spin up, spin down. So there's a nearest neighbor repulsion. And this is like an ordinary classical term that you would have from a nearest neighbor repulsive model. But what we found is that there's many off-diagonal terms as well. So this projection operator is non-trivial. And you get a huge collection of off-diagonal terms. And that's actually what we wanted to investigate and to see what kind of emergent physics comes out of that. Interestingly, if you just have this kind of term and you have one particle for every other site, you get a crystal. You spontaneously break the translational symmetry of the one-dimensional lattice, and you just get a crystal where particles want to occupy every other site. And that's kind of a classical thing, and that's actually what we found. So now I'm going to talk about exact diagonalization results and show you some emergent physics from this model. The left side here shows a classical calculation with just this term. In fact, Hubbard was the first to write down models like this. And plotting the energy as a function of wave vector, and the ground state as a crystal, just like I was describing. And if you make a move from, let's say, right to left, you pay this energy price, and you get an energy gap. That's what this gap is. And that's what you'd expect if there's no kinetic energy. Put a particle in there, it doesn't do much. There's a cost for neighbors. But what we found in this quantum model, in the flat band, that the ground states are crystals, but the excited states show a collective mode analogous to what you see in the fractional quantum Hall effect, in the sense that there's dips and peaks. What's going on here mathematically is that you're superposing all these classical configurations. And what's happening is that the off-diagonal terms generated by the projection create non-trivial coherences and superpositions, which manifests as what we're calling an emergent kinetics, because you can think of particles moving now, even though there was no kinetic energy to begin with. And that's what a collective mode seems to suggest. So this is a numerical result, and we think it's valid in the thermodynamic limit. That's this fit here. And we did an effective theory to model what was happening. By effective theory, I said there's these interaction terms, things are non-perturbative. We made non-SOTs, which is just saying, okay, there's a hopping from one site to its next nearest neighbor. There's two bands, and band 1 and 2, they cross Fermi level, green line, and we linearize the spectrum and perform bosonization of this model to check that you get, well, to see what it means and tell us that there's a Luttinger liquid there. We also check that the hoppings here in this effective model, T1 and T2, actually give us good overlaps with the exact state. So it's a good approximate model to what's coming out of the non-perturbative many-body calculation. And these linearized pieces here tell us that there's two Fermi velocities associated with the two hoppings. And as a result, you get a Luttinger liquid. So that by Luttinger liquid, I mean you do ordinary Luttinger liquid theory with the caveat that you have to find the normal modes in this 1D spectrum. But nonetheless, you get these Luttinger liquid type linearizations of a dispersion which wasn't there originally. It's coming just from the interaction. And what's even more remarkable is that you get fractionalized conductance, as you would in an ordinary Luttinger liquid theory. So if you think about the model, there's no kinetic energy. It's just an interaction. But our effective theory showed that the collective excitations and superpositions can be modeled with a linearized, approximately linearized spectrum with an emergent Fermi velocity. So the idea is that this linear mode is coming from the interaction alone. We tested whether or not this is robust. This is work, energy versus wave vector, where we included a little bit of the bandwidth, right? So the band wasn't perfectly flat. So in this context, we'd ask, what does it mean to have a flat band? And the idea there is that you have a flat band insofar as the interaction is dominating physics, and the width or dispersion is perturbing a little bit, but it doesn't tell you what the ground state is. So when we did this, we included a little bit of the bandwidth. We could check the single particle gap versus single particle bandwidth. That's what I'm plotting here. We can see what the many body gap is doing. That's the color, and we get this emergent Luttinger liquid. You expect when there's a lot of dispersion, a lot of bandwidth, where epsilon is not too small. You get an ordinary Luttinger liquid. So we saw this phase where down here, the interaction is dominating all the physics and generating this emergent Luttinger liquid. So we just, this is a sanity check that the physics is a little more robust. So there's a phase diagram in a sense. So what we found, just to add up or summarize what we got, the contact interaction in a flat band results from a projection that superposes all the otherwise classical modes. And as a result, you get emergent kinetics, so the particles can move in either direction. And this kinetics came from the interaction alone. The ground state's crystals is a crystal, but the excitations actually have an emergent velocity. Another surprising thing is that there's a fractionalized charge. This should say fractionalized. I didn't mention it, but the Laughlin state of 1/3 actually has a fractional charge. This has a fractionalized charge, as we often see in Luttinger liquid theories. I'll just briefly mention this. We found similar physics with bosons as well. We put bosons, optical lattice, spin-orbit coupling, flat band, and we projected the interaction and found the dominant term is a little easier with bosons. The dominant term is a correlated hopping term. And now you can see how the emergent kinetics can pop up here. You mean field away the density and you just have a hopping. So the hopping came there's no hopping in the original model because the band is flat. And now you get a hopping type term. And that's like kinetics, if you will, although mediated through the density. And this term in the red box here generated artificial kinetics. And so what kind of phases did we get for bosons? I don't know if you're familiar with the Bose-Hubbard model. This is chemical potential versus hopping. But in this case, it's correlated hopping, denoted by A. And for bosons, if you have a deep lattice, you get a mod insulator. And if you add an additional particle, you get a superfluid. And this is what we found in our flat band model, where there's no kinetic energy, but nonetheless, you get a superfluid. This is also in 1D, you can think of this superfluid as in the Luttinger liquid picture. And to make sure, this left panel over here is calculated by mean field theory. This inset is just what the spinner's doing. Thanks to spin orbit coupling, the basis states are a little bit non-trivial. But we did DMRG to check that we do get this similar phase transition. So this, that the mean field is showing. So this is chemical potential versus correlated hopping. And you can see there is, in fact, quote unquote superfluid, which in 1D is a power law correlation. So that's what this, this straight line showing on the log plot. It's power law correlation that you expect from quasi long range order, which means that you have a superfluid that was generated from just interactions alone. So again, emergence. So that was kind of interesting. And it's a bosonic analog of what I was just talking about with fermions. So this is just a summary of the analog features of this 1D spin orbit flat band and the two-dimensional magnetic field flat band that's generated when the magnetic field is strong. So in the first line, I'm just comparing what fields are flattening the band, magnetic field versus spin orbit coupling and Zeeman field. In a flat Landau level, you have a degeneracy associated with particles sitting in orbitals defined by a Landau problem. Whereas here, you have a degeneracy in a flat spin orbit band. In our project, we were thinking about AMO systems, so we projected a delta function or on-site interaction into the flat band. Whereas for electrons, you think about projecting a Coulomb interaction. At half filling, I didn't mention this, but 2D, you get an emergent Fermi liquid. It's called composite fermion Fermi C. What we found in 1D here is an emergent Luttinger liquid at half filling. So there's an analogy there. Luttinger liquids have fractionalized charge. You can get any fraction depending on the parameters, but it's still a fraction. You measure the charge in conductance experiments. And we know famously in the fractional quantum Hall effect, you get a discrete charge, 1/3 charge and 1/3, for example, 1/2, 1/2. So that's a summary comparison of some of the physics that popped out of the interaction when you do this projection. You have to set the problem up right so that you get quantum flat bands in distinction to classical flat bands. So I'll pause here to see if anybody has any questions about what I was talking about or how I did this before I talk about the next thing. Yeah.
I wonder for the inverted Luttinger liquid, how is it different from the ordinary Luttinger liquid, other than the fact that
Yeah, that's a really
K
good-
are different?
That's a good question. So how is it different? So I'll explain how it's different in the sense that its origin. So the equation that you get, this is an ordinary result from bosonization. If I showed that to you, you would say, oh, this is just an ordinary Luttinger liquid model, which it is. But we're using it as an effective theory that captured a tight binding model where these hoppings, like you can do Luttinger liquid theory with little interaction on this model. But these hoppings depend only on the interaction scale. They don't depend on kinetic energy. So there's no real kinetic energy in the problem. Nonetheless, the effective model of what these collective modes are doing came from, or was described by a Luttinger liquid. That was the assertion. So in other words, this is the model, okay, right there. And there's no kinetic energy, no dispersive, but we're able to construct an effective model that the only energy scale is U. Nonetheless, it's we can think of it as a Luttinger liquid in the sense that you get hoppings and you can linearize the bands and so on. So it's the same model, it's an effective model, but it's different in that its origin is coming from interactions only.
So how is it fractionalized other than that conductance is smaller than one?
That's it. This just tells you that this is what people say in that community, that it's fractionalized if the conductance is less than one. That's the lingo.
Yeah, I have a question regarding like the states of interest, because like trying to connect like 3D materials with like 1D like lattices, because for example, if you're like solving like a Hubbard like
Yes.
model, and then I'm thinking of like, you know, like iron-based transitional metal oxide, I have like the 3G, like the T2G and also EG states in mind, and like, you know, because like it's an effective model, like essentially like zooming into like, you know, states close to like the Fermi level. So I'm just wondering how to determine it for like the 1D case, like 1D lattice, like what are those states like in analogy, like what's analogous to like the EG and like T2G states for like 3D states?
Yeah, so if I understand what you're asking, so just let me explain briefly why I can talk about this as 1D without worrying about approximation, and then I'll answer your question. So what I flashed for you briefly over here was a cartoon from Emmanuel's review. Here, they can actually make 1D tubes. So they can make, so they apply a tight confinement, so it's an electrostatic confinement, if you will. Not really, it's due to lasers, but, and so it's exactly one-dimensional. So the particles can't move from here to here, okay? If you have a 3D lattice, so let's go down to here. So how do we get 1D out of here is what I think you're asking, right? Like if you have like a 3D cubic lattice or 3D material, you're asking like, how do you get quasi one-dimensional physics? Is that what you're asking?
I think what she's asking is that, I mean, she's thinking in terms of electrons in a transition metal oxide, for instance,
Yes.
and you're talking about atoms in an optical lattice. So the atoms play the role of the electrons. So
Yes.
you only have one band.
Oh, okay.
So it's like
Oh,
a
that's the question. Okay.
it's like a hydrogen chain.
Yes,
Yeah.
yes.
Okay,
Yeah.
okay, I got it.
Yes.
Thank you.
Yeah.
Yes.
Thank you. Okay, that
Okay.
clarified that. Yeah,
I
thank
see
you.
what you're asking. I didn't understand the. Thanks.
No worries, yeah, thank you.
Yeah, there's one particle in each side of the lattice, and it's very simple to think of the bands in that sense. It's actually a classic problem to understand band theory.
I have one question.
Yes.
So you mentioned it briefly, but you ignored the other terms that you get when you do the projection, which are correlated hopping.
What did we included? We included those in the calculation.
You also get exchange,
Yes, it's
ferromagnetic exchange,
all in there.
pair hopping.
It's all in there.
It's all in there?
Yeah, it's all in there, both in the fermionic calculation. So right here, it's there. It's
Okay.
inside the P.
Right.
All that stuff for the fermions. So it's got all those terms in there, and that's why.
But these are long range, actually. You know, for flat band, probably almost infinite range.
Yeah, we checked, and
yeah.
it turned out it only went out to nearest and a little bit next nearest neighbor for the delta function contact interaction.
Mhm.
You're right, but if I had a Coulomb tail, then it would be very long range.
Mhm.
So it wasn't too, there was so many terms, it wasn't obvious what the effective theory was. You're right, there were so many, but they were not localized, but quasi-localized around, so that we could keep terms that, just think about terms that were just like.
And the dominant term, yeah, I assume it's the V. And the and then you had the hopping. Okay.
So for the fermionic model, we couldn't say there was a dominant term. We just created an effective theory, had some interactions I didn't show. Here's the non-interactive part. That gave us the right answer, and we just took that as we got the right answer. But in the bosonic model, this definitely was the only term, or the dominant term by a lot. So we were able to do a quick calculation using that. So for bosons, this one turned out to be dominant by a lot. But then, as you said, the nearest neighbor term popped out from the projection.
Right. Mm-hmm. Thank you.
Yeah. Okay, I'll go on to the next section unless there's other. Okay, thanks. Okay, the last couple projects I'm going to talk about were actually motivated by feed, like some work that he did. That's why I want to mention it. It's an interesting state. So what was found a while ago, or proposed at least by Wen and company, was that you can have interactions spontaneously generate or spontaneously break time reversal symmetry, and therefore spontaneously generate chiral currents. Remember in the magnetic field problem, the magnetic field by force is chiral currents. It's an applied field. Whereas this proposal is that interactions spontaneously pick a direction for chiral currents. And it was proposed by Zhang and company that in certain lattice, particularly a honeycomb, that you can get what's called a topological mod insulator, which spontaneously breaks time reversal. And the key signature there is there's an edge chiral current around this otherwise gapped phase in the bulk. And so that was a proposal or an idea, and this would be this would show an anomalous quantum Hall effect. So this would be an anomalous quantum Hall effect. So these are some of the properties of this new proposed state of matter. As far as I know, has been conclusively seen. The idea is that you have an interaction, turn it on, a gap opens, you get a bulk gap state. It's uniform, looks smooth otherwise, but once you get to the edge, an analogy to what you would get in an integer quantum Hall effect, you get a quantized anomalous Hall effect associated with chiral edge currents. And Zhang and company proposed this in the context of a honeycomb lattice. The idea is if you put fermions there, more spin, you get a direct cone-like spectrum. And the interactions, they argued, in a mean field theory, would open a gap. However, many works, there's just some of them, went and looked at whether or not that's true, and there was a lot of debate as to whether or not the topological mod insulator shows up in a Dirac honeycomb spectrum. By Dirac honeycomb, I mean honeycomb lattice with a Dirac crossing point. But what people realize is that a better place to look for this physics is at what's called a quadratic band crossing point. So this is a cartoon of an example where you have a flat band touching a quadratic band. And it's been argued that interactions in our renormalization group sense are going to easily open a gap there. So that was the hope. That was proposed by Sun and company. And then Greg and others have looked at frustrated lattice models, and they found that this is exactly the case in what's called a decorated honeycomb lattice or a star lattice and a Kagame lattice. And they did some mean field theory there. And so we got interested in whether or not the mean field theory is accurate. So what they're saying is that the energy versus wave vector, there's many bands in the decorated honeycomb. There's 6 here. But if you come up and fill only these bottom 3, okay, you have electrons, and if you switch on interactions, the question is, can you open a gap right at this spot? Same thing for Kagame, 2-dimensional Kagame lattice. Here's a cartoon of that. Energy versus wave vector. If you fill up 2 of the bands, you're 2/3 filling of the Kagame. Do interactions open a gap there? So I'm going to be talking about exact diagonalization studies and interacting models on finite-sized systems to help corroborate Greg's assertion associated with this mean field theory. We're also going to do the mean field theory, make sure you got it right. So this is the decorated honeycomb and the Kagame. I'll start with a decorated honeycomb. So we switch on nearest neighbor and next nearest neighbor interactions. You'll see why I'm thinking about that in the context of cold atoms in a second. And the question is whether or not you can get a gap opening in this interesting topological mod insulator. So this would be remarkable because mean field theory almost never gives you the right answer in 2D. But what we find is pretty reasonable agreement. So we first did mean field theory, and the idea is that you have different order parameters, two. One is associated with the density oscillations. So these plots here that look like drawings are actually data. Each circle here represents the density in one of the many phases that we found, a stripe phase, what we're calling a pneumatic insulator, Ni, and these charge density wave phases that seem to pick out one or more of the symmetries of the underlying decorated honeycomb lattice. The other order parameter is associated with what you can call a bond current. If there's a complex amplitude to hop from R to R prime, you get a non-zero order parameter, and it's associated with a current. The quantum anomalous Hall phase, or topological mod insulator, has two degenerate ground states in interactions. Pick one, I only drew one of them, which has a particular direction to the chiral current. And the claim is that interactions, and what we found in mean field theory, for certain parameters, interactions do generate this phase. And the question is whether or not that agrees with exact diagonalization. Again, that would be shocking because normally quantum fluctuations kill interesting physics or what you're trying to do with mean field theory. But surprisingly, it turned out to be very similar. So the top panel is a result of finite size diagonalization on system sizes that are pretty much this big. I'm plotting the next nearest neighbor versus nearest neighbor interaction phase diagram. And up at the top, we get this pneumatic insulator. But at weak interaction strengths, what you can see is that the gap is opening up due to the interaction. So a little bit of interaction, both in the exact diagonalization and in the mean field theory, show this quantum anomalous Hall phase. We're able to see it. It's right there. And what's happening physically, like in terms of the band structure, is that the flat band has all these different states that are there. And the gap opens by pulling out exactly these chiral current carrying states and mixing them with the curved band. And that's how the gap opens. So the flat band was important because it donated these chiral states to the dispersive band. So I think this is strong evidence that the mean field theory in this 2D interacting model is actually, at least for weak interactions, consistent. Out here we get differences. So we found a stripe phase here, a quantum anomalous Hall phase, which with different bond currents there, something we're calling bond order here. Some of the CDW phases were similar. That was interesting too. Okay, so the physics there is that a gap's opening. But this is an abstract model. There's certain materials where people are proposing these sort of decorated honeycomb models as maybe being okay, but it's a little bit speculative to say that that would be a good model of a material, a molecular compound actually. But motivated by cold atoms, we've thought about whether or not this phase can be seen in cold atom physics. So it turns out in the Kagame context, people built these optical lattices. So you can actually shine counterpropagating beams, one in a perpendicular direction to make a 2D system, and then a few in the plane to actually create a potential, which I've drawn in blue here, which is actually a Kagame lattice. So they can make these lattices and do all the time in many labs now. And what I'm drawing in here are a special kind of atom that can sit in there. Dysprosium is one example atom with a dipolar tail, a dipolar interaction. It's not just a contact interaction. Other groups are trying to put molecules, Cambridge, and say elsewhere, rather than just a single atom. But I can just, the best case scenario I can think of are these magnetic atoms with a strong dipolar moment. So V1 is quite strong, and you can tune the hoppings and so on. So the idea is quantum degenerate dipolar fermions are also being realized. And if you throw them in a Kagame lattice, can we get the topological mod insulator physics? So this arrow indicates a dipole moment. They're all polarized, so that way there's no spin. It's hard to get this in electrons, right? Usually, unless you're in a ferromagnetic state, you don't think about polarized spins. And the dipoles are then generating this long-range interaction. The question is, does this topological non-insulator physics survive the dipolar tail? So that's something we wanted to check. What are some of the parameters you need? So we did the mean field theory again. So this is the non-interacting band structure again for Kagame. You can see the gapped point. We filled it 2/3, turn on the interaction, and this gap opens up. So this is the mean field band structure dressed by the interactions. And you can see it. What the mean field predicts is that a topological non-insulator will show up at 2/3. So that's consistent with this dipolar tail. In other words, topological non-insulator persisted in spite of this tail. So that's what the mean field said. And again, we wanted to check against exact diagonalization, and we found some reasonable agreement. So we looked at the bond current as a function of the interaction strength. And you can see the mean field theory had a very sharp transition, but our ED had a pretty sharp transition, so it's consistent. If you increase the interaction strength, we got stripes, which this kind of phase separated state, if you will, is typical when you have large interaction strengths. So nonetheless, this quantum anomalous Hall phase we predict should be there for relatively weak interactions. And then the question is, what are some of the constraints for realizing this kind of thing in an experiment? I didn't talk too much about it, but in the cold atom experiments actually aren't so cold. So it turns out I think one of the, and I know if you talk to Wolfgang or anybody, one of the biggest challenges for realizing all the many phases of matter that have been predicted is getting temperatures low enough. The experiments are isolated. So these are atoms dangling in space. There's no phonons or anything, so there's no substrate. And what sets the temperature is actually the entropy per particle, okay? And what we calculated is that you would need an entropy per particle below 0.15 kb. So this is a phase diagram where temperature is determined by the entropy as plotted as a function of interaction strength. And we get a non-zero bond current in this quantum anomalous Hall phase for these dipoles only if you're below a certain temperature and therefore below an entropy per particle. But it turns out that the entropy per particle you can get in the best labs is about 0.25, 0.2, somewhere around there. Those are in what are called quantum gas microscopes. So you have to do a lot of tricks to remove entropy. So when we plug in the numbers, we see that it's in principle possible to get up here to these low temperatures, but it's going to take a while for folks to remove that much entropy. So what we predict, if they can, is that you'd get domains of these topological non-insulators, one rotating one way, one in the other way. So that angular momentum of the experiment is conserved. I was surprised that the dipolar tail didn't completely kill this. So this is just a summary of what I talked about here. Interactions open an energy gap both in the decorated honeycomb and in the Kagame lattice at certain fillings. And you can spontaneously break time reversal and get a topological non-insulator chiral edge current. And I think one of the key ingredients was frustration. It pushed, the reason mean field theory works so well is that some of the competing phases you'd normally expect, like on a square lattice, didn't show up and they were pushed out in energy. So we got these other, we checked other, this is quite robust actually. We looked at other quadratic band crossing points in checkerboard lattices, and we looked at Yukawa and dipolar interactions, and this physics is pretty universal actually. So it's actually surprisingly robust. And by looked at, I mean we did ED and mean field theory. So this is another analogy table between the integer quantum Hall effect and the topological non-insulator. So what's surprising here, you need no external field, which is good for cold atoms because when you apply external fields, it heats things up. Whereas in an integer quantum Hall effect, you need a strong magnetic field to open a gap. Here, the quadratic band is touching a flat band. And in the integer quantum Hall state, you have these perfect flat levels that are very well spaced from the other ones. So they both have chiral edge current, non-zero Chern number, and therefore we call them quantum Hall phases. In the integer effect, the interactions are not necessary, they're perturbations. Here on the topological non-insulator, you needed the interaction to open the gap. So it's weak interaction that plays a dominant role. So it's a different way of thinking about the interaction effect. Okay, that's what I wanted to say about topological non-insulators. So I'm just going to mention collaborators that helped with these projects. Boy, who's a postdoc I had from Shankar's group and Jay's group, is now at Morgan Stanley. I was very happy about that. Like really happy. And other postdocs who are working on this, and students. And this is just a summary slide describing some of the things I talked about. One of the things that we focus on in the group is quench kinetic energy. What I mean by that's flat bands. If you're set up right, strong interaction governs the physics. So pretty excited by that. I talked about spin-orbit coupling, that can flatten the band. And then I talked about these other lattices where there's a flat band sitting near a curved band, and that can actually, interactions open a gap there. Whereas in the second project with spin-orbit coupling, the interactions were the only thing going on, and it led to this emergent collective mode that I showed you over here. Okay, this is just a last slide, so that's what I wanted to say.
Thank you, Vito, for a very nice talk. Now session is open for questions. Any questions from the audience? A couple of questions earlier. Okay, let's see if someone from the online audience.
Previous phase diagram.
Yeah, right there.
Yeah. So this one at when interaction is small and at infinitesimal temperature, what is the normal phase? Is it?
Yeah. Thanks for that. Normal phase, that's a good question. So yeah, what do I mean by normal phase? It turned out normal phase you understand at high temperature, right? So what we found is that if you just solve like the non-interacting part, you can't really, normal phase here means none of these order parameters survives. Okay, so that's what you would get if you just solve this part of the model. You know, you don't get any stripes or quantum loss Hall phase. At zero temperature, you might expect something else, it's like a hopping, the result of just having like a Fermi C, a non-interacting Fermi C there. Then you turn it up and you have excitations. This is what I mean by normal phase. Normal means all the order parameters go to zero.
So is it a featureless mod phase or is it?
No, this is like a trivial kind of phase. Yeah, that's a good question. Like if there were some interaction strike there, if we did more work, maybe you're right. Maybe there could be some kind of non-insulator that I would look at other fillings there just to look for a featureless mod. At 2/3, we didn't see anything like that. Now, by normal, I just mean the order parameters went to zero.
See, and at zero temperature at infinitesimal V1, it's still metallic, it's still quadratic band touching. And you need some.
Yeah, as it goes to zero. So, oh yeah. One interesting thing is that this thing is hard to see. It asymptotically goes to zero.
Mm-hmm.
So in fact, this line is actually connected to zero. You can't see it on this graph.
Mm-hmm.
And you can see it over here. All right, well, this is a finite size effect. So this is a finite size effect. So it doesn't go to zero because this is only 27 sites. We're just doing a finite size comparison. But what I was trying to say is that it goes like this, and like in the thermodynamic limit that we got from the mean field theory. And it actually is always non-zero. So any arbitrary small interaction opens up this model.
Because if you have Yukawa, any short-range interaction, the full Fermi interaction is always marginal relevant for quadratic band touching, and
Yes.
that should open gap. But for such kind of dipolar interaction with R to the cubic, is it still relevant for infinitesimal?
That's the claim. That's a claim that it is. That it is. That's what we're claiming, at least in the mean field theory. We didn't do any RG here, but we still found that in the mean field theory. Yeah, that's a claim. But that's a good point. You know, if you
because Yamba Kim did for the quadratic interaction R to the -4 power and show that case that would be irrelevant for small interactions.
Oh, I see. Okay. Well, for this, like I said, we just did the. So maybe you can show me that so I could take a look. But all I'm saying is that the mean field theory showed this, and it compared well with ED for cubic, for when it went over R cubed. So that was the claim. For here.
This may be a naive question, but or maybe not. Maybe you said something, but maybe I missed it. Why in this model, which has just kinetic energy and 1 to the r cube interactions, what would you expect the chiral phase?
Yeah, so as she was saying that.
I mean, I understand opening a gap, but
Right.
what about?
They're basically saying that, it goes back to the chiral phase being associated with spontaneous time reversal symmetry breaking. So the idea is that the interactions, there's two phases that can come out, and they're pulled out of the flat band actually. One is rotating left and one is rotating right. And interactions set up the situation that you have this usual situation where the interactions make you spontaneously pick one or the other rotation. That's it. But there's nothing telling you in this model that you're going to get, there's no magnetic field, there's no nothing. You just get the rotation picked out.
But usually, you mentioned the 1 to r, there, 1 over r to the 4th don't do anything.
Yes, for Yang
So even though they're long range, so
Yeah.
well, they're shorter range. So it may have to do with the range of interaction.
Okay, his interaction is even weaker. I think it's something like a quadruple interaction. Probably it's weaker, and that is why it's eventually relevant. I'm not sure for this case.
So maybe this is a critical exponent.
I do know that it's relevant for nearest neighbor and next nearest neighbor. And there's a lot of, that has been checked, okay, for nearest neighbor and next nearest neighbor. So we're just saying the tail doesn't hurt those results.
Mm-hmm.
Okay, so this is done by Sun and others in Eduardo's group actually. But, and that's why we figured the tail didn't hurt it. We just checked with Meadfield and ED. But as far as a weaker interaction or a different shape, I haven't checked. But no, it's kind of magical that the chiral edge modes come out of nowhere, but it took a long time for people to get here.
Any questions from the online audience? Anyone wants to? If you have one, please feel free to unmute yourself. Ask. Can you raise hands? Okay. If not, we thank the speaker one more time.